Now, as we start this 100-day challenge, coming up in this video, I've got the questions which are suggested for certain days to do with physics. Now, we're going to start out with a question about density. This is from an AQA paper, and you might notice in the video that I don't actually show the real exam paper. That's because of copyright issues, but obviously you can find the actual question on the website. Day number 4 it is, so 3 days later, so that gives you a couple of days to maybe do some of your other subjects. On day 4, we've got a question which is about practical skills, and also on day 7 and day 10. Now, it does not matter if you've never done these practicals before, but these are the kind of questions that you will be asked about. And as we go through this year, even if you're not actually doing the practical experiments yourself, you still have to have a good understanding of the scientific method. So that might be looking at data, maybe drawing some points on a graph, and actually thinking and analysing maybe some of the uncertainties in these results. So, some questions about practical stuff, and then on day 13 it is, we've now got a question about energy levels in atoms, so some kind of nice quantum stuff. So what you'll find is as we go through the weeks, I've tried to group questions of similar topics together and also have a range of different questions from different exam boards. Anyway, hopefully that all makes sense. So yeah, day 1, hope it's going to go okay, and then they'll be doing these videos for the rest of the challenge, so you can find about 5 days worth of physics questions all grouped together in one video, and you can obviously find that on this website. So thanks a lot and good luck. So question 5 started out quite nicely, looking at the weight of an ice cube when you've been given its volume. So what we know is that the weight is equal to its mass times the gravitational field strength. We know that its density is equal to its mass divided by its volume, and therefore we can say that mass is equal to the density times volume. And if we put this into this equation over here, we can say that the weight is equal to rho v g. So for this one here, the density it gave us in the question was 920. The volume was, and it gave it quite nicely as 4.0 times 10 to the, multiplied by 4.0 times 10 to the minus 6 cubic meters. So there's no conversion from centimeters or whatever into meters. And then the value of G is just 9.81. So if we put those into the calculator, this gives an answer equal to 0.036. And because we're looking at the weight of something, that's in newtons. So that is the weight of the ice cube. We then have the ice cube placed into a beaker. It says it displaces a volume of water causing the water level to rise. The weight of the water is equal to the weight of the ice cube. So calculate the volume of water displaced by the ice cube. Well, what effectively we're saying is that the weight of the ice cube is going to be equal to the weight of water, which is going to be our previous answer from up here of 0.0361008. So I'm keeping the data I've got on my calculator here. So that's the weight of water displaced. Now again, we know that because density is mass over volume, we can say that the volume is equal to the mass divided by the density. So the mass of water, well, we've worked out its weight. So to work out its mass, we divide by 9.81 because weight equals mass times the gravitational field strength. So the mass is going to be equal to 0.0361008 divided by 9.81. So that's now got our mass in kilograms. The density it said in the question was 1,000, which is something you probably see in lots of questions. So we're just going to divide by 9.81, divide by 1,000, to give a value of 3.68. So that means the volume is going to be equal to 3.7 times 10 to the minus 6 cubic meters. So that's the volume of water displaced. It's fairly straightforward so far, and I think most students found these equations nice and easy. Now, question 5.3 was quite difficult. I think in actual fact about 4.3% of all the students got the complete answer. So if you didn't get the answer, you're not alone. And I must say, when I read it, it took me a while to actually work out from the data they gave how to answer the question. But like all the time, a diagram really helps. So this diagram here is going to represent the volume which is basically the ice cube. So this is the ice cube over here, and the volume in total is equal to 4.0 times 10 to the minus 6 cubic meters. Okay, now within this there's a piece of iron, and the volume of that is what we don't know, but I'm going to call this unknown volume V. Okay, so that's the volume of the iron, and that's an unknown value. But we know that this thing was in a container of water, and again it's going to be a certain mass or volume or weight of water which is being displaced. Now let's use green for the water, and what we know is that the mass of the water displaced was equal to 3.9 times 10 to the minus 3 kilograms. Now, for this to be in equilibrium, we know from the previous question that the weight of water displaced is going to be equal to the weight of the ice cube and the weight of the iron added together. So what we can say is that the weight of the water is equal to the weight of the ice plus the weight of the iron. Okay, so the ice and the iron added together, their total weight must be equal to the weight of water displaced. And we can work this out because that's going to be equal to the mass of water multiplied by the gravitational field strength. And for this part here, it's probably worth remembering, of course, like from the very first part of the question, that the volume of anything is going to be equal to the weight of anything is going to be equal to its volume multiplied by the density times the gravitational field strength. So the weight of the ice is going to be equal to the volume of the ice multiplied by the density of ice multiplied by the gravitational field strength, and then the weight of the iron is going to be equal to the volume of the iron times the density of iron times the gravitational field strength. Okay, now we can see first of all that all the g's cancel, so we're going to get rid of that, that and that. We're going to put in the mass of the water, which is 3.9 times 10 to the minus 3 kilograms. Now, what's the volume of the ice? Well, the volume of the ice is going to be equal to the total volume of the cube, which is 4.0 times 10 to the minus 6, take away the volume of the iron, which is inside that cube. Okay, we're going to multiply that by the density of ice, which on the previous page was given to us as 920. And then we're going to add this to the volume of the iron, which again is our unknown. The density of iron given to us in the question was equal to 7,800. And yeah, so basically we're going to use this. So what we can then do is multiply through and get rid of the V. So the mass of the water is 3.9 times 10 to the minus 3. We're then going to do 4 times 10 to the minus 6 times 920, which is equal to 3.68 times 10 to the minus 3. Then we're going to take away 920 V, and we're going to add 7,800 V. Okay, hopefully that's all making sense so far. So then we can say that 3.9 take away 3.68 times 10 to the minus 3 is equal to 2.2 times 10 to the minus 4. And that's equal to 7,800 take away 920, which is equal to 6,880 times V. So we're going to divide this by 6,880 to get a value for V equal to 3.1976. So that's 3.2 times 10 to the minus 8 meters cubed. Now that looks like a really low number, but that's because this is quite a small ice cube and the piece of iron inside is going to be a lot smaller than that. So, sorry, 3.2, not 3.3. So it's 3.2 times 10 to the minus 8 cubic meters. That was an incredibly difficult question, and if you got anywhere within this and got some marks, then that's brilliant, because this was so difficult. But yeah, that's a lot of work to do for 3 marks. Now question 2 was about a couple of ring magnets on a wooden rod. Now you might have seen one of these at school. Unfortunately I can't have one here to show you in the video because it's currently locked down and the school that I work in is shut. But what we're going to look at is some of the measurements that were made of the ring magnet. So this is my kind of cross section of that circular magnet, and this is my digital vernier caliper. So what you can do is you can basically use this to work out certain measurements. So you might want to look at the total measurement, or you might want to look at the measurements of individual parts. So what precautions should the student take to reduce the amount of systematic and random errors when making the measurement of the total outside diameter, which is D, of that ring magnet? Now, to reduce the effect of systematic errors with a caliper, what you need to do is shut the jaws and then check that the reading is 0. And if it isn't 0, you need to make sure that you reset it. So what we want to do is you want to check that the caliper reads 0 when the jaws are shut. And if it doesn't read 0, then you need to either reset it or you need to make sure you account for that in all of your subsequent measurements. But how do we stop random error? So to reduce the effect of random error, what you can do is make sure that you take the readings at least 3 points. This allows you to check for any anomalies and also allows you to calculate a mean of those results. And it actually therefore checks that you've got the right value for the outside diameter of that thing. So you want to measure at 3 points and take a mean of those values. And that reduces the chance of having a random error in that measurement. So the caliper gives a reading of 19.32, and that's the internal diameter of that hole on the magnet. So how do we do that? Well, we use the top parts of the caliper over here, because what you can do is you can adjust this inwards and then you pull it out. And if you put this inside that hole, you pull it out until the top parts of the caliper are kind of pushing against this. So when it comes to drawing your diagram, you need to make sure that you just do a quick sketch that shows effectively the cross section of that magnet. And the inner parts here should be touching these parts over here of the caliper. So that's how you get the 1 mark for question 2.2. So these are the dimensions of that ring magnet. We've got the thickness, which has been measured as 12.09. The internal diameter is 19.32, and that's the external diameter. Now, to work out the volume, what we can do is if we work out the volume of the outside and then we take away the volume of the inside hole, we can say that the volume is going to be equal to pi d squared over 4, and that's how to work out the surface area using the diameter, and we're going to multiply that by the thickness, and we're going to take away the internal volume, which is pi d squared over 4 multiplied by t. Okay, so what we have here is the outside diameter, and we've got the inside diameter, and I've just, I could have kind of halved that, I suppose, to make it the radius, but I think this is a maybe more simple way of doing it. We can then say that that is equal to pi t over 4 multiplied by d squared minus little d squared. And if we put the numbers in from up here, that's going to be equal to pi multiplied by the thickness, which is 12.09 times 10 to the minus 3, because we're converting from millimetres to metres. Divide that by 4. Then the outside diameter is 59.90 times 10 to the minus 3, and that's squared. Take away, we'll have 19.32 times 10 to the minus 3 all squared. And this one here, it's a straightforward calculation, but just take care on your calculator that you're not making any mistakes. And this gives me an answer of 3.05255. Now the raw data here has been given to 4 significant figures, so I'm going to quote my final answer to 4 significant figures. So that's 3.0525, so that's going to be 0.053, and that's times 10 to the minus 5 cubic meters. So that's straightforward mathematics, but it's just easy to get mistaken about which values of D that you use. And also there's obviously potential for making a mistake on your calculator. So if you have time, maybe at the end of the exam, go back and just check your calculation. So all I did there was I worked out the outside volume, took away the inside volume to get the volume of that ring magnet. Now the last part of question 2.4 was about how you could carry out an experiment using this apparatus where you're adding different masses of clay to the upper magnet, and basically the student said that the force is equal to K, which is some kind of constant, over the height cubed. Okay, now this is something that you probably will never have done at school, but that doesn't matter. It's about how you can actually approach this kind of practical work to get some valid data to show that that's true. So first of all, what you can do are take measurements when that magnet is in equilibrium. And if it's in equilibrium, then the force is going to be equal to the weight acting down. Now this weight acting down is equal to the mass of the magnet, so I'm going to call that mb, plus also the mass of the clay. And that's all going to be multiplied by the gravitational field strength of 9.81. So we can work out the weight which is pushing down, which must be equal and opposite to the force, the magnetic force pushing up. So what we can do is we can work out our values of F. Now what we can do is we can choose different values of mass of clay. And what we're looking at ideally are at least 7 different values, because what we can then do is we can get some data with 7 values of mc, which we can then give 7 values of the force, and that will then also give us 7 values of h. So if we were doing this with a table, you might have values of mc, you then get your value for f, and then you could get your value of h, which is what we're going to be measuring. But we really want to see how this is related to k. And what we can think about is if we rearrange this, we can say that k is equal to fh cubed. Okay. Now, if we just plot a graph of f against h, that doesn't give us k. But what we can do is be a bit clever and say then that k is equal to f divided by 1 over h cubed. Okay, so that means if we get values of 1 divided by h cubed, we can then start to plot a graph that might look a bit like this. And when you get some data from maybe 7 different data points, ideally, if this relationship is true, we should get a straight line that goes through the origin. Now, the reason for this is that if f equals k over h cubed, then k equals fh cubed, or k is equal to f over 1 over h cubed. Now, this thing here is equal to the gradient, because the gradient of this line is going to be equal to the change in y value f divided by the change in x value, which is 1 over h cubed, and that should then be equal to our constant k. Now, if this is actually true, then we should get a straight line that does indeed go through the origin. So this would then give us a straight line of best fit. So in answer to the question, what you'd be doing is, this is kind of sort of the physics, but you need to maybe think about how you can set this out in a logical format. So you might talk about the procedure that could be used. So perhaps you measure out different values of clay and you record the mass using a mass balance. You then add those one at a time to the upper magnet. You record the values for the mass of clay added. You work out the force, and also you're measuring h. So when it comes to measuring h, you need to make sure that you're using maybe a ruler and a set square. And that allows you to get accurate values which have low uncertainty. You then plot a graph of f against 1 over h cubed. And if you do have a straight line of best fit, then that shows that this relationship up here is true. So a lot of stuff there that is quite tricky, because it takes a bit of a leap of faith to think about this equation and how that data that you might plot can actually show this relationship is true. But that was question 2.4, and again, it's about the experimental technique that we have in physics, even if it's using simple equipment but used in a slightly different way to what you're used to. In this question, we had a small steel ball that was dropped from rest from different heights, and then the time it took to land was recorded. So, how could the student use standard lab equipment to make accurate measurements of h and t? So first of all, let's think about the height. What we want to do is use a ruler, and to make sure the height is as accurate as possible, you've got to include things like maybe using a set square to make sure that it's vertical. It could maybe be clamped in a clamp stand or a retort stand. And also we maybe think about our eye level to reduce any parallax error. So these are the kind of things that you can talk about how to get an accurate measurement of height. Now when it comes to the time, what we've got is the time measured to 3 significant figures. So that's probably more than you get with just a normal stopwatch. So the way to do this in the lab, because we're using standard lab equipment, is some kind of electronic timer or data logger. So you've got to mention about how we can use a data logger or an electronic timer. And what we're then going to think about is, to get the other couple of marks, how do we start this and how do we stop it? So what you might have is, and a lot of you will have probably done this experiment, where you've got an electromagnet holding the steel ball at the top. When that becomes demagnetized, the ball drops, it starts the timer, and then it goes through a trap door at the bottom to stop the timer. So what we might think about to start the timer is we have an electromagnet, and at the end we have a trap door. So that's a standard way of measuring this time. Equally, we could have used light gates. And you can have a light gate at the top to start the timer and a light gate at the bottom to stop it. Light gates on their own is not the answer, because the light gates need to be connected up to the data logger to actually record that data. So for this one here, there were 4 marks available. In the table, complete the missing value of t squared. So this one here, we've got the value of t. So we've got 0.43, we square that, and the answer is 0.185. And it's important here that we give that answer to 3 significant figures like all the other data in that table. So 1.85 is the answer for that. We're then going to look at some data. So we've got h on the x-axis, t squared on the y-axis. So we're just going to plot the missing data and draw in the straight line of best fit. So the point just goes there like that. And when it comes to drawing my line of best fit, I'm going to be using a pencil and a ruler. 30 centimetre rulers are really important, and if you've got a clear one, you can see that there's going to be approximately the same number of points above and below the line. I think that's pretty good, so I'm going to do a long line there. So that is, I think, an appropriate line of best fit for that data. Now when it comes to determining the gradient is going to be equal to the change in y by the change in x value, and I'm going to make sure that I take points on the line. So what I'm going to do actually is just draw a triangle to show how I'm doing that. So I'm going to go from the top point up here, doing a nice large triangle, and that's going to go across the bottom as well. So your triangle that you draw, and it is worth drawing the triangle onto the graph, has to be bigger than half the length of that line. So the coordinates up here, so the y value is 0.20, and we're going to take away the y value down here, which isn't 0, but it's 0.13, and we're going to divide that by the x value, which is equal to 0.97, and we're going to take away this value here, which is equal to 0.64. So it's just worth taking time to actually make sure you've got the right coordinates here. So 0.2 take away 0.13, divided by 0.97 take away 0.64, and this gives me a value of 0.21. Okay, so I think that to 2 significant figures is an appropriate answer to give my gradient. So now we're going to use some SUVAT equations to show that this relationship is true. So for the ball which is dropping, I'm just going to write down S, U, V, A and T. Now the height that it drops through, the vertical displacement S, is going to be called H. We know that it was initially at rest, so U is going to be 0. The acceleration is due to free fall, so that's going to be equal to G, and T is just T. Now we're not concerned with the final velocity at this point. So which equation can we use that doesn't have a V in it? The one we're going to use is S is equal to UT plus a half AT squared. So that's my SUVAT equation. We're then going to start realising that basically U is 0, so this term goes to 0. I'm going to replace the S with H. That's equal to a half times A, which is G, times T squared. And because we want to make t squared the subject, we're going to multiply both sides by 2. So we can say that 2h is equal to gt squared. And then we can say that t squared is equal to 2h over g, which is the equation that we have up here. So that's just showing where this equation comes from. Now, use your answer to C part 2. So we found that the gradient m was equal to 0.21, and that's what we found from the graph. Now, whichever value you've worked out, that's the value you're going to use. So this is the gradient. But the gradient, because it was a change in y by the change in x, was equal to t squared divided by h. Okay, but it also says over here that t squared is equal to 2g times h, and that means t squared over h is equal to 2 over g. So what we're really saying here is that our gradient is equal to 2 over g, and that means that g is going to be equal to 2 divided by our answer for the gradient. So I've still got the gradient saved on my calculator here. So 2 divided by the answer gives a value of 9.4. So using my value for the gradient, I've got the value for g as 9.4 meters per second squared. And that's kind of what we're expecting. It's going to be a value in the order of 9.81 meters per second squared. Now for question 15, we had an experiment that you might not have done, but it doesn't matter because we had a balloon popping and then we were recording the sound here and here and looking at the time for the sound to get from this point to that point. So the first bit is we need to criticise these results. So what could they have done better? First of all, there were no repeats. So that was an easy 1-mark question. I mean, you might have said, for example, that maybe the range was too small because it only went between 1 metre and half a metre, when they could have taken maybe a bigger range of values, so going up to maybe 1.5 or down to 10 centimetres. Other things may be that they could have measured the metre distance to the nearest millimetre rather than the nearest centimetre, like they did there. So quite a few things you could have done for that. The second part was 4 easy marks, because all you had to do was plot a graph of this data. Now all of you know how to plot graphs, it's just straightforward stuff, but don't forget the basics. Make sure that your plotted points cover more than half of the area of the graph. Now we don't need to go to the origin, so we don't need to go to 0, so I'm just going to go from 0.5 up to 1, and the separation goes from 1.5 up to 3.2. So let me just think about some suitable scales. So I've gone from 1.5 up to 3.5 and 0.5 up to 1.0. Don't forget, of course, that what we need to do is make sure that we label the axis. And my time over here is going to be in milliseconds. So then it's just a case of putting in some data. So 1.5 is over here, and then 0.6 is 1.9. Just made a couple of mistakes there, but that doesn't really matter because I've got, I'm doing it in pencil. So we've got 2.1 over here. So that's my points plotted. I'm actually using A3 paper, so even my 30 centimetre ruler doesn't quite fit. But on the actual exam, your 30 centimetre rulers would have been absolutely perfect. So let me just estimate here approximately the same amount of points above and below that line. So I'm going to do my line like this. For part 2, we need to determine the value for the speed of sound in air. Now, effectively, what we've got on this graph here is a distance time graph, and therefore the gradient is going to be equal to the velocity, okay? And that's going to be equal to our change in y divided by my change in x value. So what I'm going to do is on my graph over here is I'm going to draw a line as big as possible so I can then actually work out my change in y and change in x values. Okay, so and again, it just takes time to just make sure you read off the right values. My change in y, we go from 1.00 up here, and again I'm reading to the line, not to the point that was plotted. And we're going to take away down here 0.505. The change in x value, we went up in this case to 3.15, and we're going to take away 1.50. So that's the data I'm going to use. And not forgetting, of course, that on the x-axis we've got something in milliseconds, so that's times 10 to the minus 3. So that's a simple mistake you just want to avoid. So let's do that. And this gives me an answer equal to 300. So the speed of sound in air was 300 meters per second. And again, depending on how well you drew your line of best fit, they allowed values between 280 and 310. But it really depends on the graph that you drew. So this one over here, nice big graph, an appropriate line of best fit, and I worked out my speed of sound by taking points off the line of best fit. But it does say here that the actual speed of sound in air is 330, which is a value that you might be familiar with. So what we need to do is comment on the value of the speed of sound in air at this temperature compared to the student's results. So we can say that the student's value was lower than the true value. So the first thing I've done, I've just commented on the student's results. So that's an important thing that you don't want to forget. So the other thing is about why could that be? Well, it could really be due to the distance measurement or the time measurement. So it might be the distance wasn't measured to the same position on each microphone. There might be perhaps some parallax error. So there might be an error in the measurement of distance. That's something to comment on. The other thing was about maybe the measurement of time. So maybe the measured time is too small, or maybe there was a large percentage uncertainty in those results. So for this question here, to get the 3 marks, you want to make sure that you comment on their value and saying if it was lower or higher. You want to talk as well about measurements for the distance and how there might be mistakes in the distance, as well as errors in recording the time. So that was that question. Question 3 starts by looking at some energy levels for a hydrogen atom, and what we have are transitions, and this is when the atom is de-exciting. So maybe we've had an electron which has been excited, and then as it drops down energy levels, it then emits photons that correspond to the energy gaps which are on the diagram in the exam paper. So the first question looks at the transitions shown here, and it just wants you to match which of these are either ultraviolet, visible or infrared photons. Now for this one over here, what I'd say is that we've got to think about the frequency or the energy of these different sorts of radiation. So visible is going to be in the middle, and I suppose actually without thinking too much, because if we look at the length of these arrows, B is in the middle, that means that B must be the visible one. Okay, so that's not even a physics question, that's more like a logical thing. But effectively, ultraviolet is more energetic, and that's when we're going to have a higher frequency photon, and that means we're going to have a bigger energy gap. So what we can say is that C has the biggest energy gap. It's going to give off the highest energy photon, which is going to be ultraviolet. And then that leaves, I guess, infrared as A, because this must be infrared because it's got the smallest energy transition, and therefore it's going to have the lowest energy photon. So that is 3 part 1, and that's hopefully a straightforward 1 mark question. Now I thought that question 3.2 is quite tricky because there are 2 mechanisms in which we can excite the electrons. One way is that a photon with just the right amount of energy can be absorbed by the electron, and then it moves up an energy level. The other way is that it could be excited maybe by collision with another electron. So we've got electrons colliding with electrons which then excite the atom. And the question is really about why the photon has to have an exact amount of energy, but the electron can have a range of energies. So this one here, not many students got everything correct. So this was a difficult question. But basically what a lot of people said was about the photons. So with the photon, all of the photon's energy is exactly absorbed by 1 electron for the electron to move to a higher energy level. Okay, so that's what we know about photons. They must have exactly the right amount of energy for that to move to a higher energy level. But it's a different mechanisms for electrons, because an electron that comes in can just transfer part of its energy to this other electron, which moves up an energy level. And then this might lose some of its kinetic energy, and it might move off maybe at a different angle or at a different speed. So what we can say about electrons is that the electrons can transfer part of their energy to cause excitation and then keep moving. So hopefully that explains why for a particular transition the photon must have an exact amount of energy, but the electron only needs a minimum amount of kinetic energy, and if it has more kinetic energy than is needed for that transition, any energy not absorbed by the electron moving energy levels, this electron will still have, but it's just going to be travelling at a lower velocity afterwards. Okay, now let's get into some proper stuff with the photoelectric effect. Question 3.3 is looking at the photoelectric effect and the energy of the photons emitted in the previous part of question 3.1. Now, in terms of the photoelectric effect, it's given us the threshold frequency, and that tells us then about the work function of cesium. Now the work function is going to be equal to hf0. Okay, so that's Planck's constant times the threshold frequency tells us the minimum energy required to liberate an electron from the surface of that material. So this is going to be equal to 6.63 times 10 to the minus 34. That's Planck's constant that you can find in the data book. And we're going to multiply this by the threshold frequency of 5.1 times 10 to the 14. And this gives an answer equal to 3.3813 times 10 to the minus 19 joules. Now, on the previous question, it had the energy levels given in electron volts. And what we therefore need to do is convert from joules to electron volts. Not forgetting, of course, that 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. So I'm going to take this value here. I'm going to divide it by 1.6 times 10 to the minus 19 to get into electron volts. And that's then equal to 2.1 electron volts. So photons that have, so basically if the photon energy is greater than 2.1 electron volts, then the photoelectric effect happens and we get photo electrons. Now, looking at the photons we had in the first part of the question, the transition from this level to this level, well, it's going to be equal to the change in these two values. Now, for the first one, it's just 1.5 take away 0.85. So the change in energy is 0.65 of an electron volt, and therefore A won't happen. The transition for B goes from 1.5 to 3.4, which is 1.9 electron volts, and therefore B won't happen either, because the photons here don't have enough energy for any of the electrons to be emitted by the photoelectric effect. But this transition here, well, actually we can see it's clearly going to be bigger than 2.1, and 13.6 take away 3.4 is 10.2. I probably didn't need my calculator for that. So C, the photons have 10.2 electron volts, which is greater than the work function of cesium. So for this one here, we can say that the photons emitted by transition C would have enough energy to cause the photoelectric effect, and therefore electrons to be emitted from the surface of cesium. Now, the last part of the question is actually quite similar to many other examples I've seen on previous past papers, but lots of students found it difficult because it was a two-step calculation. Now, the first thing to remember is that the energy of the photons is equal to the work function plus the maximum kinetic energy that those can have. And therefore, we can rearrange this to say that the kinetic energy of the electrons, which have been emitted because of the photons being incident on that metal, their kinetic energy is going to be equal to the energy of the photons take away the work function. And that's equal to this value here, which is 12.1 electron volts. So that's the energy of the photons incident, and that's what's given to us in the question. And we take away from that the work function, which is what we calculated in the previous question, which was 2.1. And I'm going to use my previous value that I calculated of 2.1133. So I'm not going to use my rounded down number. I'm actually going to use the number that's saved in my calculator. Now this then gives us an answer of 9.986666 electron volts. But that means, that's all good, but we need to convert it into joules to work out its kinetic energy. So what I'm going to do is I'm going to multiply this by 1.6 times 10 to the minus 19 to give an answer of 1.598 times 10 to the minus 18 joules. So that's the kinetic energy of the photons. But we know that sort of the electrons, but we know the kinetic energy is equal to half mv squared. And we want to find out how quickly they're going, or their maximum possible speed. And therefore v is going to be equal to 2ek over m. We're going to take the square root of that. So I'm going to take the previous answer, multiply it by 2, and divide it by the mass of an electron, which is 9.11 times 10 to the minus 31, that you get in your data book. And not forgetting to square root it, this gives us an answer equal to 1.873, which I'm going to say then is to two significant figures, like the raw data that we had. I'm going to say this is equal to 1.9 times 10 to the 6 meters per second. So this is all fine. All we're doing is we're looking at the energy of the photon, take away the work function to find the kinetic energy. converting it into joules, and then using it in this equation here to rearrange it to make v the subject, to find that the answer is 1.9 times 10 to the 6 meters per second. So pretty quick.